It's already time.
Yes, please.
Yeah, hi everyone. Today we are going to see the live session for that week 8. So this session will be handled by Devesh Singh. He is also one of the course team support. So over to you, Devesh.
Okay, thanks, Amrita. So hi everyone. I think this is the session where we will be discussing about activity questions and all that, and you can ask your doubts and everything. And then I think tomorrow we have this solve with instructor session, right? So let me share the screen. And so is my screen visible to everyone?
Yes, sir.
Yes.
It's visible then.
Yeah, okay. So I think many of these activity, first we'll go through these activity questions, and many of these activity questions are already part of the video lectures. So I think I will just ask the questions and you can sort of turn on your mic and tell the answer, and then if there is some problem or some doubts, we can discuss that. So this first question, support vector machine is dash learning algorithm. Is it supervised, unsupervised, or reinforcement? So any one of you can say the answer.
It's supervised learning.
Yeah, it's a supervised learning. We all know that because we need labels for finding the hyperplane. Then next question is support vector machine is a dash classifier. Supportive, discriminative, generative, and agglomerative.
Discriminative, but I was quite curious to know what agglomerative even means.
What? Sorry, what?
It is discriminative, but I just was curious to know what does agglomerative, the last option, what does it even mean?
Okay. So this question I made, I'll tell you what this thing is. So actually there are only two types of algorithms, discriminative and generative. The other ones like just framed it in a way so that people get confused because it's a support vector machine, so people might think supportive and things like that. Otherwise, when we talk about agglomerative clustering, so it's actually a hierarchical clustering technique which you will study, I think, in the 11th week. But here the main distinction was between discriminative and generative. I think in the first lecture itself, it is being mentioned that it's a discriminative classifier. So can any one of you tell what is exactly this discriminative classifiers is?
It looks at the various features, the samples, right, and tries to identify the mapping between the samples and the labels and try to discriminate. Basically, the way it will figure out the differences between the samples and thus predict the label.
Yeah, exactly. So see, the reason why the name discriminative have arrived is because the root word is discrimination, and that's what exactly these kinds of classifiers do. Rather than actually coming up with the distributions, underlying distributions in the data, what they do is they try to, whatever test cases you have or whatever data you have, they try to discriminate it or differentiate these two. So so even this SVM thing, you actually have a hyperplane, and the way you label your, or find out the output is the points or the data points lying above the plane are positive, or lying below the plane are negative. So it's trying to sort of discriminate or differentiate your data points. That's why it's a discriminative algorithm. Even logistic regression and other things, they are also under this category. So next, moving to SVM is termed as dash classifier.
Sir, and what is generative, just for the completeness of it?
Okay, so just I said that discriminative does not really talk about the sort of underlying probability distributions. So generative algorithms, they try to focus on obtaining the underlying distributions. So that is how they, and more rather than these generative algorithms, we are mostly using while generating data. So if you, I don't know if this course does have that statistical component, but in statistics, we usually
we do have the we study Bayes, all the
Bayes is one generative algorithm, but usually for data generation and all, we usually use. So we are given certain distributions, and we have to generate data as per the given distribution. So that is where we use generative algorithms. So next thing is SVM is termed as dash classifier: minimum margin, maximum margin, optimum margin.
Maximum margin.
Maximum margin. And why do we call them as maximum margin classifiers?
It is trying to make the boundary so that the support vector, you can say the boundary, it has to be maximized to cover all the you can say the data point.
So what happens in algorithm, as this SVM algorithm, as you have seen, that we first try to identify these support vectors, right? And then we try to draw planes around that. The actual the last output or the desired hyperplane is somewhere in between, exactly in between these two margins. And this classifier or this algorithm is focused on sort of enhancing or maximizing the distance between these two margins. And once we do that, we actually make sure that our two samples or two classes or two labels are far apart, so that the error tend to go down. So that is why we are so one of the aims, or one of the way we obtain weights here is by maximizing the margins between the by maximizing the margins or the distance between the two margins. So the next question is again very simple. The training examples that are closest to hyperplanes are called as dash.
Sir, before we move on, I have a question. Can the bounding planes be intersecting, or they always have to be non-intersecting in nature?
They cannot intersect.
It has to always make the equal distance between them. Then only we can consider as SVM algorithm.
I mean, the ones on which the support vector for each class lies, those two lines. So they always should be non-intersecting. Right?
Yes. Right.
Okay.
And if in fact, if you see, sorry.
No, that may be for binary classification. I don't know whether there are three labels, three classes. I don't know whether they will be intersecting. I actually had the confusion. I want to ask.
For multiple labels, then we go for that one versus all and all that approach. Na? So that's altogether a different story, right?
Yeah, I couldn't visualize that, whether they can even visualize the SVM or where the support vectors will lie in a multi-class classification. But yeah, in this lecture, I think Sir talked only about the binary class.
Binary classification. I was saying something. I don't know what I was saying. I forgot. Just give me 1 minute, right? Regarding this thing. I don't know. Okay. When it will come to my mind, I'll. Okay.
And just one more doubt, because as Renisha said about classification, it came to my mind. We are not covering regression as a part of SVM, right?
Yeah. In this, I don't think even in next weeks or things like that, this is being covered.
But it's used in normal practice, right? I mean, or how is it?
I haven't used it the usually all the problems that I have done.
Okay.
So.
Okay. Fine.
I mean, that depends what you want to do. So basically, to be very honest, if you go to industry right now, I think most places, even you have this two things coming up. One is interpretability, where they are actually using very basic models, where it's easy to sort of get the understand the models. And on the other side, very delicate deep learning things, because for computer vision and things like that cannot be done with these basic algorithms. So
Okay.
Yeah, just additional point. See, support vector regression actually is not covered in the course because this support vector regression also tries to fit a hyperplane such that the maximum points, no, the data points tend to lie on that plane. So that is the actually concept behind the support vector regression. So in classifier, we try to fit a hyperplane such that two different classes are maximally separated. But wherein in regression, where we used to predict the continuous valued outputs, this SVR tries to find a hyperplane such that that hyperplane holds all the points so that we can further predict the points that lie on that hyperplane. So that is the concept behind support vector regression. Since we have moved on from regression to classification, we didn't want to introduce regression into this week. That's why we have not considered this regression. I hope so. You can carry on, Devesh.
Yeah.
Thanks, Amrita.
Okay, so the next thing is the training examples that are, I think we discussed this, right? That are closest to hyperplanes are called as dash.
Support vectors.
Yeah, support vectors. So they are like the basis of this algorithms. In SVM, the goal is to find the equation of a hyperplane such that first minimize the margin of the training data, maximize the margin of the training data.
Maximize the margin.
And that's why they are called MMC, maximum margin classifiers. The next is again pretty simple. The distance between the two margins is given by which of the following expression? Norm of W square, 2 upon norm of W upon 2, or 2 times norm of W.
Over norm of W.
Yeah. So I think the derivation is also pretty simple. Next thing is SVM can be used to solve regression problems as well.
Yeah, we just discussed that it is yes, but yeah, we are not doing it in this course. Yeah.
Yeah. Okay. Next thing is a soft margin SVM modifies the constraint from hard margins by allowing some points to violate the margin. True or false?
True.
Right.
That's true.
Next thing, when C is large, SVM is influenced by outliers.
True.
And why is it true?
Because it will try to overfit the data. So in that case, it will try to fit the outliers as well.
Yeah. So when actually C is large, the regularization is very less. And because less regularization, there is overfitting. And overfitting is like just moment you have new outliers or new data points, it will try to even fit into that. And that's why, yeah, it is influenced by outliers. Next is the loss function that helps to maximize the margins in case of SVM. It should be in case of SVM is which of the following? Recurrent loss, entropy loss, cross entropy loss, or hinge loss?
Hinge loss.
Hinge loss, right? So you all know the graph of that hinge function, max of 0 and 1 minus t, right?
Yes.
Just out of curiosity, the name hinge comes from the plot of the function, is it?
I have no idea about that.
Okay, no problem.
Looks like that. I mean,
yeah, it looks like that because I was trying to understand.
It is hinged at 1, right? Yeah, that's what you would call it.
Yeah.
It's hinged at 1.
Yeah, because even in the case of ridge and lasso, I was trying to understand why they give such names in those case of regularization.
Oh,
okay.
Next question is, when C tends to infinity, there will be overfitting. True or false?
Yes, true.
This I think we just now discussed that when C will be very large, as C tends to infinity or becomes larger and larger, the regularization becomes lesser and lesser, and that's why this problem of overfitting comes in. So this is true. This is again very basic mathematical question. The projection of a vector onto another is obtained through which of the following operations? Dot product, vector addition, cross product, or difference of vectors?
Dot product. Yeah.
Yeah.
So this is the basic of the kernel, right? Yeah.
The next thing is, yeah, this is very obvious question. You have to look at the data and say whether it is linearly separable or not.
Actually, it didn't seem obvious because you can draw a line, but they are not linearly separable as we have defined them.
Why did you say it is not obvious?
No, just see, if you just say I can actually draw two specific lines that separate the points, right? But of course, they are different lines, right? It has to be a single line. So that way, it is. I thought it's a nice question, nicely worded question. So
yeah, like a hyperbola. So hyperbola will, I think, kind of separate.
No, actually,
it's linearly separable.
Yeah, it is linear because I can draw a line, just above the bottom axis and just below the top axis, and that actually will be a linear line. I think almost parallel to each other, but that way they are linearly separable, but not in the actual definition.
So, I mean, there are two. I think the definition of linearly separable is very well formulated in terms of mathematics, right? So, if you have a set of points P and a set of points N, then we call the, set of points, these two set of points to be linearly separable if we are able to come across a vector W, so that any vector in P, say PW and P or NW, the sign of these two should be different. So that is the definition. So the W remains the same. You don't have to, sort of draw two lines. So that's why even if you are able to, put two lines and separate them, that's not the definition of linearly separability. I think this question meant single thing, right?
Yeah, I mean, I answered it, but I just said that you mentioned it's a straightforward question, but I thought made us think. So whoever came up with the diagram, I think they did a good job.
Okay. I just copied it from somewhere. I think Google or somewhere.
I think this is a typical case. This is where the perceptron failed and the whole theory
that was, I think, in the that's rhombus thing 0 1 1 1 1 minus 1, something like that.
Yeah, correct. Same thing, no? This is similar setup.
Yeah,
only thing is we have multiple points here.
Actually, what you are saying is very interesting story. I hope everybody is aware of that story. So this particular question, I don't know who posed this problem, and the reason why he posed this problem is that single perceptron cannot handle this kind of data, and hence we need multiple layers of perceptron to answer or to come up with things. But this paper or something which he wrote had such a negative impact that it literally led to the sort of AI winter, and that's
Minsky and Papert or something.
Yeah, they developed this XOR problem where this XOR function is purely not separable linearly. This is also a kind of an example for XOR, where in XOR the upper 1 1 and 0 1 1 also there will be a 1, and 1 0 it will be 1. So at that time you cannot separate them linearly through a line.
Yeah, they are moving up. Actually, the green zeros, they are moving in hyperplane, and then you can put a plane and you can cut it. That's why he has explained it.
Yeah.
So I think these are next. So which of the following is the RBF kernel? Hello. Yeah.
E to the power minus x minus y.
Yeah.
Then the first one is actually linear.
Sorry.
The first one is actually linear.
No, it's polynomial.
Polynomial.
Okay, it's n is the polynomial. Sorry.
Yeah. So I think this answers the second question also. Which of the following is polynomial?
Polynomial, right? It's n is there,
Okay.
right?
So let me ask you one question, because this polynomial thing came up. So if I have a kernel, say kxy, which is defined as the inner product of x comma y to the power 2. This is one kernel, and the other kernel is 1 plus the inner product of xy whole to the power square. So what is the difference between these two? I mean, what will be the resulting factor? So what kind of features transformation will these two lead to? Because in both the power is 2, so it will be quadratic, but what will be the difference in these two types of kernels? Is my question clear?
Are you asking about the second problem?
First one is xy.
So consider any of the problems. Say first, second problem, right? So in second problem, this is the polynomial kernel, right? I give you two choices. First is, if I make this C0 and n equal to 2, we will have one sort of polynomial kernel, right?
Right.
And in second case, I make this C to be non-zero, say 1, and the power to be 2. In both the cases, it's sort of quadratic kernel. What will be the difference?
I think origin won't be there.
Right.
Only the intercept, right? So the first one will pass through the origin, second will not.
More than origin.
Not.
So no, I mean, that is a different thing. But the kernel transformation, why these two are very interesting, is if in case you put C is equal to 0, you actually say if there are features, say x1, x2. So the resulting features that you will obtain will be x1 square, x2 square, and x1, x2, all quadratic in case when the C is 0. But when it is 1, you actually also obtain what you call features of lower degree power also. So if you sort of do this cubic,
okay,
then
yeah,
in that
that'll
case,
be
the linear
pure
and,
polynomial, yeah, pure second
yeah.
degree. This will have mixed of degrees, 1 degree also, yeah.
Yeah. I think I made this point clear to others as well. If this is clear, then that's okay. If it's not clear, you can sort of put your questions. What exactly did you did not understand?
So second one leads to something called basis expansion, is it? Like we consider all powers of the features and formulate the transformation, is it?
Yeah. But one thing I want to say, why you use that word basis here?
No.
Basis for polynomial, you are saying.
In linear regression, like when we discuss the polynomial transformation, we actually take the combinations of each feature to the particular power, right? For example, if x1 and x2 are two features, we take x square, x1, x2, and x2 square also into the polynomial. So that is like we expand the features that is termed as basis expansion, right? In the linear regression context.
I'm not sure about the terminology.
I think it's called polynomial transformation, not the basis expansion, I think, because you are making the new features. It's a feature.
One thing, I mean,
when we are making the new features, we take the combination of the features to the particular degree, such that every term has the same degree in effect.
Right.
Square x1, x2, x2 square, so
and x1 square.
And x1 square. So this is what is called. This is what is termed as basis expansion somewhere. I read. I'm not sure.
Okay. Maybe I'm not
Even
sure.
I'm not sure about it. So, what did you say? Basis or basic?
Yeah, that is actually
basis expansion.
Basis function, right? We, for example, we take 0 and 1 as our axis, or 1 and 1, 0 for two-dimensional space.
Oh, so this basis you are talking about from linear algebra.
Yeah, like that he's telling.
Okay, then what he is saying
Yeah.
is wrong, because for basis you also will need to have a lower degree polynomial. I mean that
Like,
depends. Basis you
yeah.
can have anything, that you have to first define the space, and the space will decide what kind of basis you have.
Yeah,
So,
there is like that. He's telling that in that sense, what he's trying to make sense is if two features x1 and x2 is given to us, we are considering that as a basis features and then trying to bring up the other higher order terms using this x1 and x2, right?
okay.
So in that sense, he's considering this to be a basis expansion.
Okay. So, the point is, what I want to mention here is you cannot differentiate these two by that basis wala name, because each of this will be basis to some of this space. So that is what I want to clarify here. Okay. Next we move to Mercer's theorem. So I think you all are aware of that. Kernels in case of SVMs are very important, because they save you a lot of time and complexity. And so this theorem, basically Mercer's theorem, is one theorem that actually helps you to identify which of the following functions could actually be considered as a kernel. So not every function qualifies to be a kernel. There are multiple conditions. Some of them, I mean, out of these four, which of the you think should this function satisfy in order to be a kernel? Hello.
Sir, if you
You
can
said
explain that
continuous and
feature again,
differential.
because even in the Discord, I think there were some comments saying that they didn't get the kernel part, kernel concept.
Okay. What exactly do you want? Okay. Let me start by this. What happens is, so the reason why this non-linear SVMs and our polynomial regression varies is this. What we did in polynomial regression is simply what we did is we transform the features, right? From, if we have only say two features x1 and x2, we transformed it to x1 x2 x1 square x2 square or x1 x2, things like that. And then we followed the regular process. And the same could be done here also. We have seen that after doing certain transformation on the data, if it's not linearly separable, that transformation actually maps your data points to another space, and in this different space these points become linearly separable, right? So this could have been approached in a very similar way, just like it was approached in the case of polynomial regression. You first do a transformation, you end up in a different space where the data is linearly separable, so you apply the usual SVM thing. But what happened is, these operations, first transformation and then applying SVMs is very costly. I mean, the number of computations go high, I mean, very significantly are more. So this kernel concept, what it does is, if you have done computations by hand of SVM, all you need is the dot product, right? S1 S2, if S1 S2 S3 are what you call support vectors, all you need is their dot product, S1 S2, say S1 S1 or S1 S3, things like that. So what this kernel trick helps you is to obtain those dot products in the newly formed space in terms of the earlier space. So that is how the computations are saved. So whatever I said, does that make sense to you? Hello.
No, I have a question. So when you said dot product, the entire derivation of the maximum margins was actually done using the normal dot products, right?
Yeah.
But you're saying that in previously couple of minutes back, you said that any valid dot product can be used as a kernel function.
Say it again.
And the dot product, whatever we have this component wise multiplication and adding, that is one dot product we can we are used to in the linear algebra, right? But when it comes to the radial basis function, or this is a different kind of dot product, right? I mean, this Mercer's theorem, in the context of Mercer's theorem, a kernel is something,
Wait a second. I think the confusion is there are two different things. Kernel is a different thing, and these transformation functions are different thing. So you, I think in future questions we will first come across. There are transformation questions. I'm sorry. There are first the transformations. So these transformations actually project your points to different space, and these kernels are, sort of that actually help you to identify the the inner product in the different space in terms of the previous space.
Yeah, we talk about inner product spaces and all, right?
See,
so the question is like whatever the kernel and the inner product, the concepts are they tightly coupled with each other, isn't it? So how can we understand this? Probably that is a question asked.
Understand.
I mean, how can we extend the normal dot product notion into that inner product space and understand these kernel function transformations?
Okay, so I think we have to go to some basics for that. First is this, this inner product thing, not all the spaces are inner product spaces. First we have to understand. So there is a hierarchy of spaces that we have. So that at the bottom you have something called as vector spaces, where there are certain properties about vector additions and scalar multiplication and things like that. Then you move to further higher spaces where this notion of inner product makes sense. So the reason is, and then even if you move further, there are better spaces, which what we call as Hilbert spaces and things like that. The thing is, whenever we think of these spaces and all, the first things that come to our mind is R1, R2, R3, and things like that. And these are very beautiful, elegant spaces in the sense that they have all the properties there, but not every space. So is this your question?
No, my question is, see, we all the derivations, everything we talk about, talk in the context of normal dot product, right? So, but when it comes to the inner Mercer's theorem,
definitions and all we talked about in terms of inner products.
Correct. Inner product means like the dot product is
one of the inner products.
Correct. All the derivations are done based on that, right? Whatever we said, the 2 by norm of W, these are all understood. These are all used to derive these formulae, right? But when it comes to Mercer's theorem, it becomes a little abstract, right?
Yeah.
So how do we actually translate this understanding into that? I'm not sure if I'm asking my question is clear. In the context of Mercer's theorem, it just says inner product kernel, right?
Yeah.
So so how this dot product as an inner product can be understood in terms of inner product kernel? I think that is where the confusion starts, for me at least.
So can you put this precise question in the forum, and then I think we can see.
Actually, hi, Nisha. I have just probably it's not exact question, but for this SVM concept, I'm not able to relate in terms of matrix matrix computation. So if we can take a simple example to start with, simple one vector with a x and the y and the predicted vector, and let's calculate that. Can we do some mathematical calculation to just relate it? Because
I think in some of the questions here we have that. We will do that.
No, I'm just asking if you can take a fresh example with just travel all the journey of this SVM concept with a single vector example, just to relate all these concepts. Because I'm not able to.
We will do that in today's session. Don't worry.
Okay, fine.
We'll take So I think, your question, I think you put it in the discussion part discourse, and then I think we can we'll look into it, because even I think I am not exactly able to understand what you want to say. So I think, or maybe I don't know. So maybe I think in today's session we might be able to clarify that question. I think when the questions transformation things will come up. But yeah, so let's come back to this question, and then we will maybe later on go into that. According to Mercer's theorem, the function, this kernel function, should satisfy which of the following properties? So this is just part of the theorem.
So yeah, so it should be
continuous is there because it's a polynomial, so continuous is there. I'm not sure, and I don't think it will be differentiable in all the.
It should be symmetric in arguments.
Yeah. So answer to this is continuity and symmetry in arguments. Then next question is, let us consider two vectors A and B and apply polynomial mapping. The dot product of the transformed vectors is equal to the square of the dot product of the original vectors. It should be applying polynomial, I thought quadratic polynomial it should be. So what is the answer?
Yeah, it's actually true.
True if we actually think of this as quadratic, but if it's
of course.
Yeah.
Oh, it's a polynomial only.
So let's move to next questions.
Now, what is the answer for that? Can you please explain?
I think it should be false because it's talking about polynomial mapping. So for polynomial, so that's the question. I mean, thing I was discussing. What you do is, rather than taking the dot product in the new space, that kernel happens to be the inner product in the previous square of the inner product in the previous space, the original space. So that is what the dot product of the transform vectors is equal to the square of the dot product of the original vectors.
No, but how is it possible? Like, for example, in your example, you just said, let's say 1 plus x whole square, right? So 1 plus x, you are discussing the context of a polynomial to the power of n, right? So 1 plus x whole square, it translates into 1 plus 2x plus x square, right? But the vectors in the transformed space are 1 root 2x and x, right? They are not the independent transformed vectors, no? I mean, they do not map directly to one-on-one, isn't it?
Yeah, this is false. So there are multiple kinds of, even when you talk about quadratic transformation, there could be multiple kinds of, and you can actually derive the relationship in each case. It is a one-to-one. That is why the kernels are interesting. So if you properly define your kernels and there is proper transformation, there is always one-to-one correspondence. That's what makes the computations very easy. That is what I'm trying to say, that this correspondence is actually one-to-one.
No, can we split these two steps? No, you said let us consider two vectors A and B and apply polynomial mappings, right? So what do you mean by that?
Multiple. It could be multiple. It could be, say, simply taking C to be 0, or it could be taking C to be 1, 2, or even putting 1 or 3, something like that. So corresponding to that, so each time you define a different mapping, there will be a different kernel which will result in this one-to-one mapping.
No, in this example, what are the two vectors in case of that 1 plus x whole square? What are the two vectors A and B there as per the question? How
it will not depend upon the vectors, it will depend upon the transformation.
Actually, what we're doing, we are taking taking vector A. Okay. If you're putting any polynomial transformation, then you're multiplying with, again, you are doing a polynomial on B. And if you take A transpose B, finally what will get, you always will get A transpose B whole square. Because anyway, it is going to multiply. Whatever polynomial transformation you apply, finally it is going to multiply due to the transformation. And
I know
finally,
there are a lot of doubts. Just once we come to the questions and all, I think I'll be able to clarify all your doubts. So just hold on till that time.
Okay.
Okay. So yeah, next question. Which of the following is the equation for Hinge loss?
max 0, 1 minus t.
Exactly. Straight true or false? Hinge loss is differentiable at t is equal to 1.
No, it's false because it's a there. It's corner.
Yeah, it's a vertex or corner point sort of thing. So the left hand derivative and right hand derivative won't match, hence it's not differentiable. Next is consider the below statement corresponding to soft margin SVM demonstrations. Large value of C implies large margin. Small value of C implies a small margin.
Yeah, both are false, right?
Yeah, exactly. Both are false. Can anyone explain why both are false?
Overfit, if we have a larger C, it will overfit.
And hence there will be lesser margin, smaller margin.
Right, but about slower, but if we less C, is it underfit or?
Yeah, sort of, there will be higher regularization. Not exactly underfit, but yeah, so it's similar that you have to work out some optimum value of C where there is not too much of overfitting or underfit. So but this lower value of C implies a larger margin, so this small and large has been interchanged, so both are false actually.
Okay, can you please explain the concept of overfitting here in case of SVM? In case of linear regression, we said that the model will overfit when it tries to learn more. It is trying to fit only to the data that is at the hand, right? The function will actually run through all training points, right? Whereas in case of this margin model, margin separator, so we the size, the width of the margin increases is controlled by the value of C, right? So why are we saying that? What is the concept of overfitting and underfitting here? If width of margin is more, then the errors will be more, right? Because like we will not be able to classify each point perfectly, because there will be some points that will be falling inside the margin, and thereby we will not be able to classify them properly. Where is the notion of overfitting here?
Actually, this loss function has two components. One that tries to so you have to also keep track that there are you are actually able to separate the two classes, and then second will take care of so one will take care of the weights and the second will take care of this the distance between the margins. So when the larger the margins are, your actual hyperplane lies just in between, and then since this these margins are obtained by separating or segregating these 2 points, so we try to come up with those equations in a way that I mean that equation, that w dot this thing is greater than equal to 1 and less than equal to -1. So in that case, when the margins are larger, this
so when margins are larger, the loss is more, right? We are doing more misclassifications.
No, because why are you saying that we are doing more?
Because see, in a tighter margin, you are perfectly separating, most of the points, positive points will be on the positive side, negative points will be on the negative side. But if the margins are increasing, the positive points may fall into margin band, and thereby they get misclassified, right?
Something which lies in the margin band will surely not be misclassified, because the classification is done with the help of the hyperplane. So just because something lies within the margin and it will be misclassified is a wrong notion.
Oh, I see. Okay. So, but then
because you see, the last thing is what you do is sign of y dot all that. So that actually says that everything. So these margins are just a tool to obtain that hyperplane. All that classification is done in terms of hyperplane only.
Correct. Okay, then in case of overfitting, in linear regression, we said overfitting was there because the training error was low and test error was high. Right. Now here in this case, the training error will never change. That means, right? It's not the derivative of the margins. Irrespective of the margins, the loss will always be same. You're saying, because the separation is done by the hyperplane itself. So margins are not going to play in misclassification in such case. Then the loss will always be same. Where is the notion of so the training error will not change based on C, right?
No. So actually a follow-up question. Does C, having a different C, does it change the shape of the plane? I mean, the orientation of the plane?
It will change the orientation of it.
So that way it will classify, it will create more or less fewer errors. Right?
Yeah.
No, we just said, yeah, we just said C is not going to play a role in misclassifications.
No, he said hyperplane.
Yeah, just a second. So let me just clear you the notion of using the C here. See, the hyperplane is purely dependent on your data points and the weight vector, that W1. And why we use the C is hyperplane is the center boundary that initially separates your two classes. And this margin is, we have two bounding planes, each one for each of the classes, one for positive class and another for negative class. So this margin is the distance between these two bounding planes, such that they are separated nicely so that no data points fall within the margin. So that is what is the exact definition for your margin. So when you have this C parameter, that is for soft margin SVM. In case you consider the hard margin SVM, there is no influence of C parameter, because these bounding planes are strictly do not allow any points to fall within this plane. But in the soft margin SVM, we are allowing some data points to fall within this, say, both of the bounding planes. We provide the slack variables. I hope you might have seen in the sir's lecture. So yeah, these data points, these are influenced by this parameter size, slack variables. So we call them as slack variables. So these slack variables correspond to those data points that fall within this margin. So what happens when you have this C value to be very large? So C is inverse of regularization, right? C parameter. So what happens? Your bounding planes only get to reduce because the margin becomes less. The width of the margin reduces when you increase this C. When you decrease the C, that is when you do not have any value for C, just equivalent to that of a hard margin. So that's such that your boundary is big. That is, the margin is high. So that is why this equation is actually to let you understand the value of this C parameter. So why we call it as underfitting or overfitting in the sense, you are going to make this misclassified points fit within this margin. So that is why we call them as underfitting or overfitting. So if you allow them to be fitting inside this margin, we call them as, if you allow more number of points to fit within this margin, then that is overfitting, right? Many points may fall within the margin. So this may lead to future error while making predictions. The points will fall within the margin. So that is why we call, that is why we use this C parameter for defining fitting, that is underfitting or overfitting in SVM.
No,
Unlike in normal regression.
Isn't the tighter margin is overfitting rather than the broader margin?
So tighter margin in the sense, see, tighter margin will run almost nearer this main boundary, right? The separate hyperplane.
Correct. This main boundary is only for this training data. Actual test data may have a different boundary.
Yeah, so actual test data may fall within the boundary or may not fall within the boundary.
Correct. By learning a tighter margined hyperplane, are we not fitting more closer to the training sample and thereby overfitting?
Yeah, we are trying to see what I think in lecture also sir trying to show you that difference between fitting this C, changing the C value to large and changing the C value to less. Yeah, we are imposing the criterion for this points, right?
No, correct. So my question is a tighter margin overfitting is synonymous to overfitting or broader margin synonymous to overfitting?
You're asking in terms of this margin and value of C, right?
Yeah, exactly. So because in earlier question also, when the discussion about C came, it was related to the overfitting and underfitting notion. So my question is, if we have a tighter margin, then that means the hyperplane is only modeled for this particular training sample. Thereby, I was understanding that it is overfitting, because if another sample comes, this hyperplane, whatever we learned from the training sample, may lead to more misclassification. Whereas if we are having a broader margin, then thereby we would allow margin of error.
We will allow more data points.
So I was thinking like
okay.
Tighter margin is overfitting rather than the broader margin is overfitting. So I just wanted to get the better understanding of it.
Oh, okay. Actually, this tighter margins go overfit, right? That is what you're claiming.
Yeah, that is how I understood it. If it is margin is very tighter, then that means the hyperplane is only learning about this particular training sample more. And thereby...
correct. Yeah, in my sense, so that is what actually I was also trying to say. I am trying to say in the sense, with respect to C. So, in tighter margin means your value of C should be large, right? Large value of C will lead you to tighter margin.
Yeah.
Am I correct?
Yeah.
So that is the case, correct.
Okay, but in that case, in this question, large value of C, large value of C implies tighter margin, is it?
Yeah.
This is
false,
right?
Na?
Both the statements are false, right?
Okay, got it.
I think we have not confused others.
So my understanding is correct, whatever I said. If we have a larger C, then we have a tighter margin, and thereby we are overfitting. Correct? Okay, right. Thanks.
So others are clear about this concept or this notion. I think if you see the video, sir is actually trying to use different values of C, and the new margins are being even displayed in the video. So that will, I think,
that is correct. What I'm trying to understand, how does it relate to overfitting and underfitting? That is the
Yeah, see, one final thing what I would like to say is, you are talking about the points that are falling inside the margin. So when the margin is very less, that is within this nearer to this separating plane alone, what happens? The other data points that are residing into the other classes, they say somewhat away from the margin. So these are all classified under correctly. So classification will be correct for your training set. So when your margin is very small. So so at that time, more data points will be classified as their class alone while training. So when testing occurs, so at that time when a new point falls within the margin, at that time the model will not be able to generalize well. So that is the main concept for overfitting, right? Your model will not generalize for the unseen data.
Yeah, got it.
Yeah, correct.
So let me put it in other words so that others also understand. So what happens is when the value of C is very large, these margins actually come very close to it. So when these margins are coming close to it, they are actually avoiding misclassification. But then since the aim of the SVM is to have larger margins so that the classifications would be better for the upcoming examples. But now when value of C is small, it is able to manage very well in the training data, because margins are very close and it's sort of able to distinguish the two classes. But this actually is not favorable for the test data, and that's why we are calling it as overfitting. So is it all right? I mean, does everybody understood what I said? Or are there any other
questions?
It is
understandable. Okay. We can move on to the next lecture.
So this is again, this is very simple question. Consider the two code snippets, and which of the following is RBF kernel and which of the following is a polynomial kernel.
The first one is RBF, second one is
Okay. Then Amrita, where do we have to go after this?
Yeah, so now we have completed this activity questions. So we can move on to this practice questions.
Okay. So here I think we have examples and we can sort of
So after this, we can go through the programming practice questions.
Achha, we go to programming practice questions.
After this, completing this practice questions.
Okay. So first question is, in hard margin SVMs, maximizing 2 upon norm of W is equivalent to which of the following? Achha, answers are also there. Let me expand this. I don't think it's so, but I'll be able to hide the answers. So what is the answer to this?
Now also answer is visible.
Yeah.
Now it's
So is equivalent to which of the following?
Mod of W square, right? That's one I can think.
Minimizing, maximizing.
If it is, yes, it's a minimizing, yes. So if 2 by lambda is maximizing, then lambda square will, lambda, I'm saying W square will be the minimizing.
Okay. So C is correct. And
also, if you minimize this W only, then also you are going to maximize, because it's.
So the answer is B and C. So the only logic I wanted to put forth here is, say if we have a quantity, say 1 upon K, as long as we want to maximize this entire expression of 1 upon K, we have to reduce the value of the denominator. So whenever in the denominator we minimize the denominator, the entire fraction goes up. So maximizing 2 upon W norm is equivalent to minimizing norm W or norm W square. So both B and C are the answers. So next question is,
is minimizing norm W square same as minimizing norm? Do we understand like that?
Actually, yes, but the reason why we go for norm square is because we want to remove that under root. So otherwise, both of these expressions are there. So in I think a lot of problems that you solved in high school where you want to find the maximum minima. So you sometimes sort of you to square. So square and square root both are on positive side are increasing functions. So increase they are equivalent. Maximizing w and x and x square are same as long as x is positive.
But optimization characteristics will change, right? For example, this norm square weight norm square and these two figured in lasso and ridge, right? So when we had objective function with the norm square,
wait. Lasso ridge differed in terms of the norm we use. So one had L1 norm and another had L2 norm.
Correct.
So norms are different.
Correct. So here also norm just this one norm is it is not that.
So what I'm trying to say here is so forget about lasso and all these things. Mathematically, if you want to,
it's just a square function.
Yeah. So this is keeping in mind the mathematics. So it's not norm 1, norm 2, it's usual norm. And mathematically, if you want to decrease or maximize this sort of fraction, what you do, you sort of, minimize the denominator. That's what the question is.
Okay.
And the norm here is same. I mean, otherwise that norm 1, norm 2 thing we write below.
Oh, this in both cases, this is L2 norm only.
Yeah, whatever norm. It could be L1 norm also. But it will remain same. What I'm trying to say.
Okay.
So next question is, which of the following statements are true about SVM?
First one is correct. Hyperplane changes if any one of the support points, vector points is removed.
C is not because it is not the part of support vector. So hyperplane change.
And D is correct, I think.
Okay. So the point to emphasize here is any changes in the support vectors will influence the hyperplanes, and any change in the vectors which are not support vectors will not influence the plane. The two things that we need to keep in mind while doing SVM. So the entire location of the hyperplane is influenced by the support vectors. So that is. So let's move to next question. So suppose that we have these 8 data points and the labels are given. So we have to identify the support vectors. So here basically you have to plot them and identify the support vectors. Or you can use some algorithm. But I basically thought of plotting. So can you identify the, I think it will take just 2 minutes to plot. Or should I skip this question?
No, we can try.
No, we can try.
Okay.
Yeah, please help to draw it.
Sorry?
If we just draw this.
See, consider these data points as x1 and x2, and the labels you just have it as -1. So you have like xy coordinate system. You have x as x1 and y as x2. So 2, 1, you plot a point, and 2, -1, you plot a point. So you have some two different structures for two different labels, right? For -1, you plot a 0, and for +1, you plot a plus symbol or likewise. So you try to plot these points such that you get the points which are nearer to each of the classes, right? So those are the support vectors. The points that corresponds to each class, when their separation is very less. Or if you plot, then you can come to know how we call them as support vectors.
Okay.
Yeah. Simply you can plot in a pen and paper also. Even in paper also you can plot.
I think it will be A, B, D.
Okay. BD.
A, B, E. What is 5, 1. That is 4, 0 also, right? For me, it is coming D only, not E. Now I think you need to draw. Okay, let's wait other.
Yeah.
I got it as ABD.
Okay.
Yeah, getting AB because for all the positive you consider all are greater than 4 in the x-axis. 4, 5, 6, 5. Okay. So
Okay.
it can be 5, I think.
Yeah, hyperplane is coming as a vertical line, right?
Right. Yeah. It's crossing 2, 1 and 2 minus 1, and this is coming 4, 0, right?
Yeah, so this line passes through 3, I think.
Yeah. Hyper.
0, 3, 3, 0.
Yeah, 0, 3. Yeah. Yeah.
3, 0.
3, 0. Right. Agree.
I am also cutting ABD. I think the answer is wrong. ABD is the right.
Yeah, right.
Yeah, 2, 1, 2, -1, and 4,
Oh, yeah,
0.
it's 4, 4. Yeah, maybe.
Yeah. I think the option answer is written wrong. Support vectors have. So should we move ahead? So this is one numerical problem that I think will solve the doubts. Consider the following data set, and we have to find the weight vector and the value of b, right? So I think some of you, I mean, one of you was asking this, right? How to do hand computations. Hello.
Yeah, I think Nishant was asking.
Yeah. Hi, Nishant. Are you here? Hello.
Yeah, sorry. Yeah.
So this is the kind of question you wanted to ask, now, how to do hand computations.
Yes. So yeah, so I wanted to know if I have this vector in hand, then how we can calculate all the losses like hinge loss, or then how the margin, that. So the whatever the probably see earlier professor used to describe this in terms of examples, so I can relate myself. But probably these things are not there in our lecture. So if you can help me on that.
Okay. So I think there are so this way of solving there are two things actually. So when we have talked about code, right? So in code we have not solved it in this particular fashion. So if you do hand computations, you ultimately what you do is you identify the support vectors and you sort of form a system of equations to identify these alphas, and then the value of alphas you actually compute alphas and the support vectors. But there, when we have actually done this code, we have actually used the gradient descent method to identify the weights, because what we have done is ultimately the aim is to come up with the values of W that sort of minimize the loss. And since we already have the loss function, and we know that gradient descent actually helps us to minimize it. So these two are actually very different. So here also, so we can sort of write the loss function and then calculate the derivative and all that, but the approach here that we have used is different.
Right. So that's what, see, I understand. See, the computational maybe probably I'm not getting into the end up to the calculations. We just wanted to see how it started, right? Well, okay, this is the vector problem. So this is the formula that we applied, and it will be calculated like you have to transpose, you have to take a dot product. So up to that point, if you can just showcase, I will note it down for our reference. So because this SVM concept, I'm not able to understand it. So that's why. At least you can just see, you can, if it's my perspective, that you take a vector, then calculate the margin, and then just write down the one-liner code that, okay, this is the code will do this. So I'm just trying to relate those things. So because programming assignment, I'm not able to solve. So these vector probably will help us. So calculations, one-line formula. This is the, like np dot maximum of t, 0 into t minus 1.
Okay.
That's the formula for vector, for hinge loss.
Okay. So
but then how apply this?
Yeah, I'll tell you this. What you do is, whatever your question is, we will be actually having the solve it instructor session tomorrow, and we will be discussing all that in detail. But since you have asked this question now, I'll just give you rough idea of how we go about this problem.
Yeah.
So so the hinge loss is actually max of 0, yi into wi plus x plus b, something like that, right? These two.
Yes.
Yeah. Now this is a function. This is your loss function. Now your loss function could be actually 0 or this yi dot something, right? So first you have to actually write this condition that whenever this particular value is greater than equal to 1. So when the particular value will be greater than 1, which means that your loss function is actually yi dot something. Otherwise, your loss function is 0, right?
Right. Correct.
In case of loss function is 0, you don't have to do anything. But when your loss function is this expression of yi into wi x plus something, then in that case, as per of your what you call gradient descent, you have to partially differentiate it with respect to w and b, right?
No, so now probably I'm confused. So up to that one I understand, but again when we do this computation, that if you can just put on a paper, receipt, then probably let's see if I can understand. Otherwise, if you are discussing on tomorrow, that's also fine.
Okay, let me quickly go through it once, but actually we'll be sort of discussing it tomorrow as well. So this is your loss function, right?
Correct.
This is so yeah, this is your loss function, right? And now you have, let me show you the condition. Okay. Oh, sorry. This is not. So this is actually your condition. Give me a minute. I think it's taking time to load. Oh, taking too long. So this is your function, right?
Yes.
It's max of 0, a. So when will this function be 0 and when will this function be this? When this function is greater than equal to 1, then in that case the value of the loss function will be this, otherwise it will be 0, right?
Correct.
So you have to frame this condition in the code, and if this condition is there, so this is the place where we have evaluated the condition exactly, right? So when the condition holds true, then you have to differentiate it with respect to, so this is the expression of the derivative. So if that is 0, so the only thing you have to worry about this part. So you have to differentiate, and what you will get is 2 lambda w. So that is 2 lambda w is actually what you are updating in your w. Similarly,
no, sir, I'm not able to understand. Sorry, but can you just take a snippet of these two codes and run it on a different collab book to just see that in terms of calculations, like the unit test, right? Something. I'm
so
just
this
thinking.
we will do it tomorrow. Just
okay. Yeah. No, sure.
Okay. See, this is very simple. You just have to differentiate. Once you have to take this as 0, and other time you have to take it this expression depending upon what your condition is violated or not. And then simply you have to differentiate it with respect to w and with respect to. So we are not differentiating it in our code. What we are doing is we are actually using the expression of the derivative, which is this. So if you actually, this is the expression we are using.
Okay.
And depending upon that, we are updating w and b. So this is the expression of the gradient under this condition and otherwise. So you see now, when this this thing becomes 0, the derivative you are left with is only w, 2 lambda w.
Right.
And if this is non-zero, then the derivative will also be yi times xi. So this is this expression, additional expression, w times.
Yeah. So yeah, correct. So we will. I will try to again work on this tonight, so at least I can well prepared for tomorrow. Okay. Sure, thanks.
So yeah. So I think so that was one method. The other method is this, where what you do is you are given the data points, and what you identify the support vectors, and then by you have to solve this system of equation. By solving this system of equation, you will actually get alpha i's, and with these alpha i's and the support vectors, you can actually find the weight. And once that is done, once you have weight, you can now predict any other upcoming point. So is this clear?
Yeah, this I just see that. Yeah, I will see this probably. You are uploading this document, right?
I think yes. This is your these are your solutions. So yeah, we'll probably.
So always we have to go by the diagram then to get the support vector if it is not given.
See, since these questions were meant to make you do hand computations, so that is why we did
Okay,
it.
okay.
Otherwise, in code, I mean, that is not possible. Even see, this is only 2-dimensional. If you go in higher dimensions, then it is practically not even possible to visualize. So you have to find I think in the week 11, when you will be doing clustering and all that, so there will be different kinds of linkages that will be taught to you. There you can actually, have a method of identifying.
No, this we have study in the MLF always and on math too also. Adding
Okay,
the
so
by.
you can find the minimum.
Yeah, that we
Yeah.
know.
Okay.
-1.
So you can identify. Yeah, good. So next question. I think this is again, Amrita told me that you have already covered in basics courses, Lagrange multiplier method.
Just one question. Sorry, why you're putting equals to in the third equation? So
Which
the two support vectors are on the positive sides. There were two equations are equals to 1 and one is on negative sides. That's why you're putting equals to -1. Right?
yeah. So that
Okay.
depends upon the label. So here S1 will if S1 is negative, then it is -1. Here S2 is positive. Relabeled, that is why +1.
S1, 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 S2, and S1, S3.
So this will be because of S1, and this will be because of S2, and this will be because of S3.
Okay, thank you. Yeah.
Okay. Then I think this I think you can do. Do I need to do these things, or you are already have done Lagrange multipliers in earlier courses?
Yeah, this we have already done.
Okay.
You can, if anyone has problem, then they can raise, but I think we know this.
So next question is, if we have two kernels, then the sum is also kernel. This is again mathematical questions and can be proved. So this is the question which I want to focus. Now you ask questions. I mean, if we start deriving the expressions, I think things will become clear. So here what happens is, let me take, have we given some example? So okay, we'll go step by step. So can you answer question number 8? Hello. Am I audible?
Yes, we are reading.
Can you? Okay. Sorry.
So when you say XY, right? So you said it is a transformation from R to R3, right?
Yes.
So this is plain and simple. You can understand. This looks like a polynomial transformation, right? But the question is, what do you mean by when you say suitable kernel? You said f of x and f of y. What is this y?
So just like you have fx is equal to 1 under root 2x comma x square, fy will be 1 under root 2y comma y square. So that is what there also I said, transformations and kernel are two different things. So once you read this question, you will understand that this f is actually a transformation, which is taking your point from R to R3. And then we will see what is kernel here. And then we'll try to relate all that inner product dot product things. So is everybody trying this question, or like few people?
No, we're trying to understand the question in first place. When you say it is suitable kernel, Should we check for some properties of the kernel here?
No. So see, a while ago I told you this thing, na? What is the purpose of kernel? I told you that since there are two ways, what we used to do in polynomial regression is we used to transform the features, and with the new transform features we used to apply regression.
Correct.
Now in SVM what we do is here also we have to transform the features, right? Now
Right.
if you see this regular problem in here, so what are we actually trying to do? Here we are actually taking the dot products, right? So for solving a SVM problem, what we need is we need this dot products. So one way is you transform the features, and in the new feature space you take the dot product. That is one area, one way. But that leads to higher calculations. That will, once you solve it, you will understand. The second way is you find a suitable kernel, and this kernel, what it will do is it will actually give you the dot product of the new transform vectors, but in the terms of your original vectors, in the terms of the dot inner product of your original space. So that is what I meant by suitable kernel. So kernel is suitable. I mean that one property is there, continuity and all those conditions, but here it is, which will actually help you to map these one correspondence between the inner product.
So here we have to take x as x and y as x, and we have to expand these to these polynomials. Is it correct?
Yeah.
Like in first case, it will be x dot product x whole square. It will be x square to the power of 2. It will be x to the power of 4. Right? That is the I mean, in the if f of x is a vector 1 root 2x x square, if we
Just
have
a second.
to,
You
this
just try it. Just try it on your own, and then I'll just reveal the solution in a minute. So let others also think about it, because
is it the thought process? What is the correct thought process here?
Yeah, I'm not allowing you to do this think aloud here, because otherwise, if you start thinking aloud, people will sort of follow your lead. That is, I'm really sorry for that, but
yeah, no problem. No problem. Yeah.
since we are short of time, should I start doing it?
Yeah, Devish, I think it's better
if I start.
Just explain.
Yeah.
Please
Open
explain.
this PDF in browser. I think you can annotate on the PDF. You want
I
to write
think this
anything on this
Adobe will
PDF?
also allow me now.
No, what we actually do is we used to open this PDF in a browser and share that browser so that through Zoom itself we can annotate on the
Okay,
PDF.
that is a
So,
better option.
yeah.
Which browser? Any browser will work, right?
Any browser, Edge or anything.
No, it will work only in Edge, not in Chrome.
Edge, okay.
Oh, Edge only.
Edge.
Yeah, Edge, they have given inbuilt feature.
Okay, I see. I mostly
Because
use
this
this
Zoom
Edge.
is Microsoft ka.
Yeah, in Zoom, we are not, I think we cannot annotate on Zoom screen. So,
Yeah.
so here you can draw.
Okay, but I don't have a writing pad. You have to bear with this bad handwriting because I have only this. So we have fx, right? So f of God, difficult to write. F of y will be I don't think I can write like this. Amrita, can you write or?
I think you can. Okay, then I'll write.
I think we can talk through, right?
Okay,
So
yeah.
f of y will be 1 comma root 2 y comma y square.
Y square, exactly. Now, can you find this inner product by simply the dot product? So this expression, can you find?
Yeah, that is 1 plus 2x square plus x to the power of 4.
1 plus, no, it will be 2
xy. 2xy plus x square plus y square.
Plus x square, y square.
Oh, we are talking in terms of y. Okay. Yeah.
X square.
Y square.
And y square. God, this is too difficult to write. So this will be the expression, right? Now, since your x and y are in, R, so their inner product is simply their product, right? So if you expand this expression, what will it be? It will be 1 plus same like this, right? 1 plus
1 plus 2xy plus x
yeah,
square y square.
X, y.
Okay. I was trying something more.
Now you did you realize that your xy k of xy or this expression is actually these two things are same, right? Now this looks just a mathematical manipulation, but it is very powerful in the sense that see now just for this transformation, what you have to do like 2-3 operations. So this is just for transforming the space. This is 3 operations for fx, 3 operations for fy, or maybe more operations. Now when you find this dot product also, you have to perform lot of what you call operations there, right? But rather than doing this, you could have actually used this kernel, which actually expresses the dot product of the new space. So this is actually the new space. fx and fy are your new transform vectors. X and y were your original space, and fx and fy are vectors in your new transform space, which is R3. And you have to find the dot product because SVM, that's the demand of SVM. So rather than doing that, what your kernel is helps you do is it actually gives you an expression where this inner product is in terms of your original space, which saves you a lot of computations. So that is the power of kernel. So that is the fact I want to emphasize. And this kernel thing and this transformation are two different things. In fact, this function is from R cross R to R positive or R positive union 0. So that is the thing. So I think all the doubts that have been accumulated till now are cleared now.
Can you please repeat that? This kernel is from what to what?
R cross R. Your original space ka cross product R cross R, because it will take X is from R, Y is from R. So in case this original space have been R2, it could have been R2 cross R2. And what it gives you is a real number. So this is actually R positive union 0, because or no, it's it could be actually R. It has to be R, not R positive. because this is the expression in terms of inner product.
Whereas original inner product is also inner product is also from R cross R to R, right?
Yeah, that is not the question. The question is this kernel is actually I'm trying to first differentiate this transformation function with respect to K. That is one thing, and second thing, I'm making sure that this kernel is actually giving me the inner product in the new transform space. These are the two things.
And always the kernel is in terms of the original inner product.
Yeah.
Okay.
And you can practically see how many computations we have solved. And if you actually go with this question, you will further realize how powerful this is. So see, we are here from R3 to going to R9. So this itself is very expensive computation. Then once you obtain this, you have another vector Y. And again, you have to take the dot product, which further complicates things. But here, I think the answer is this. So you can directly do this. So simple.
So in a way, the transformation, the f of x that we have on the top, right?
Yeah.
The nature of that transformation is governed by the kernels we have, isn't it? Kernels are actually defining the what kind of transformations we can actually achieve on the features, right?
I think what you said is opposite. So see, kernel is something which we have to find. I mean, even first we have to identify which kind of transformation actually segregates it. And then depending upon the transformation, we have to obtain some kernel expression.
No, but how do we know, like root to
that is here? How to know which kernel we need to take?
No, polynomial is like, for example, 1 plus x square is like a plain and simple polynomial. Do we have, we apparently don't have a straightforward kernel for it, right? We have to have this root 2 or some coefficient, then only we will have a suitable kernel, right?
Okay, your question, I understood. So both these questions don't have any fixed algorithms to find. So these are the popularly known things. So you actually do transformations keeping in mind the already existing transformations. You don't sit and each time devise it. I mean, you could do that, but it's not very easy to do. So mathematicians have already worked on these transformations and kernels, and they have given you that. And in machine learning, we directly use that. Or I mean, coming up with these transformations and finding the kernels corresponding to them is a very challenging task. That is another thing.
So in a way, we do not have a kernel for pure polynomial transformation. We can have a kernel in case in something like looks like polynomial transformation, but it's not exactly polynomial transformation.
What exactly you meant by polynomial?
I mean, the polynomial transformation which we studied in week 4, right? 1 plus x plus
no.
Square.
I think we have that. I think this A will do that job.
Okay.
But so that is
one is not there.
This
constant
10th question. But you said of same degree, na? Here the degree is 2.
No. In polynomial transformation, we have 1 plus x square like that, right?
Acha. That I think x1, corresponding x2. To that also we have. We can find actually.
No, Govind, that is actually we are adding it degree 1, degree 2, degree 3. Then only we. I think he's only talking about a particular degree.
Correct.
The thing
Let's say I have a degree
2. You can actually manipulate this number, and you can actually put a constant here also, and that will actually give you different kernels. And I think one of them can give you that. So you can also manipulate this number.
Because I'm just seeing that root 2. I'm seeing how to get rid of that root 2.
Yeah. So that could be very challenging, but yeah, you can get. So while making the questions, I did not think that much that you will be asking all these questions. So otherwise,
I am also thinking how to know that which kernel is going to be take this one.
So that is what I'm telling you. There are no fixed algorithms of finding it out. So I think whatever you asked is clear now, right?
Yeah.
So
Okay.
We studied only two kernels right now, right? One is that
three.
Radial basis, this one, and
linear polynomial and the RBF radial basis.
So apart from that, what kind of other kernels we may have? Maybe
there
just you can by name. Maybe you can
there is one kernel. So if you know Andrew Ng, right?
Yeah.
So his
Yeah, yeah.
videos are there on SVM. I think the last video, the last portion will tell you the name of many of these kernels. And after telling the names, he also says that we never use all of them.
Okay.
We only use these popular ones. I think one of the kernels I remember is string kernel.
Oh, I see. Okay.
And I don't know what that is. And he says that. And I think there was another kernel he mentioned, which is by the name of some distribution, probability distribution. I don't remember the name.
Oh, I see.
So yeah.
Okay.
I think this 3 is covering a lot of cases like our polynomial transformation, linear, and that RBF is considering, I think, all the symmetric, that Gaussian and everything.
RBF looks like very simple, but it is actually very complicated because what do you know what RBF does? It actually maps your data points to infinite dimension space. I don't know what that means.
Okay.
So yeah.
No, but
We have
in
not
the
reached-
in the initial weeks, we said square root of x can also be a transformation. Log x can be a transformation.
Yeah.
So those things, log x, square root of x, they can be achieved by these kernels.
I am not sure.
Okay.
Oh, log is used to reduce.
See, maths mein this question is very important. So something cannot be done is very difficult to answer because you have to eliminate all the possibilities. So even the proofs you write where you prove non-existence of something are very complicated compared to proving the existence, because a simple example could prove the existence of something. But to prove the non-existence of something, say for example, if I have to prove that corresponding this transformation of log x, there is no kernel, it will be a very complicated problem.
Exactly. You have to take all possibilities and say.
Yeah.
Okay.
And now I understood why SVM is this much complicated. SVM.
No, actually, you are going into too much complication. The simple idea, if you just try to see that why kernels are useful, just because they give you the inner product in the new space in terms of the original space, I think you can settle it down and you use the existing kernels, because trying to find out new kernels and all is beyond the scope of this course, right? That is like pure mathematics, statistics, PhD sort of thing.
Oh, that's why they say that in transformed space, inner product should be defined.
Yeah.
No, I got it. Thank you. It's clear now.
Yeah. So I think, this one question, So now again, I should not have put this question because this will sort of further enhance your what you call doubts, or maybe so the question have been framed only to make you do computations, but this is not the exact way we tackle problems. So can you read the question?
11 is it?
Yeah, 11.
Basically, you're asking to transform these points into this new space based on this condition.
Yeah.
And then find the fit SVM and find the support vectors, right?
Yeah. So this is not the way we do. So actually what this, that is what I told you, in regression, polynomial regression, what we used to do, transform and then apply SVM. So in this case, since it's a toy problem, the dimensions is less and the computations are not so much. So what, and just we have to make you work how, this transformation is done. So that is why we are actually making you do the transformations only, and then rest of the things are working in that space only. Because after transformation also you are in R2. So it's a transformation from R2 to R2. So that's why you are doing it. Otherwise, the other approach is followed.
Other approach means that inner product approach.
Yeah.
Okay. So this is not an inner product, and this is not a practical way of fitting a SVM, you're saying.
Yeah.
Okay.
But it will work here because the transformation is from R2 to R2. So I think everyone should try this problem.
So are you saying if there is no kernel, let's say the kernel is so when SVM is introduced, kernel was not introduced, right? We only talk in terms of transformations, right?
So I don't know about the history, but machine learning, a lot of things that have happened were actually existing, but people realize it later on that this particular mathematical concept can be used here to simplify things. So I think here I am sure that these kernel things and Mercer theorem were existing there, but people then employed them in tackling these problems.
Okay, no, my question is, even if we do not apply a kernel in the way that you explained in problem number 8,
yeah,
but still it is considered as a transformation, and SVM is still a valid approach to do the build the model, isn't it?
yeah. You can find the you can find the answers to without even using the kernels.
Right. But the question is, how did we come up with this transformation is something that is out of
yeah.
Why? What? There is no reasoning for why a transformation should be like this, right?
No. So there are some. So you cannot come up with things very easily, but some intuitions. So a lot of mathematics is built upon intuition and then making it concrete. So a lot of intuitions. So if you try to plot these points now, so they are sort of let me see. They are sort of this. Some points are here, and the other points are outside this, right? So that gives you a feeling of trying to put all these points somewhere here, throwing somewhere here. So you know that this is a equation of a circle, so you sort of just put either one of them, keep one of these points intact and transform the other points to somewhere, say sort of translate the other points. So sometimes these things can be intuitive. So a little intuition can actually help you to come up with these transformations. It's not that random.
Okay.
So in this case, this is happening actually. What they are trying to do is, this is a circle. So points that are confined within circle or outside the circle are being pushed away and the remaining are kept away. So if you see that if I move the points on one of these circle to some distant place, I'll be able to separate them linearly. So that's the thing that is being done here.
Yes, within the within the circle they are left as it is. Outside the circle they are moved outside.
Yeah. Or other easier trick could have been, if I have to move these from R2 to R3, these pot of points which are outside the circle should have been given +1, and the points that are within the inner circle should have been given as -1 in the z axis. So that also you can very easily separate points.
Right.
So what are we doing now? Are you guys trying this problem or should we move ahead?
I think calculations will take some time.
Yeah, so you can do it and maybe tomorrow we can discuss.
Yeah, sure.
So this is the last question and then we move to programming questions. So I think dash are sometimes used when classifying test documents or DNA sequences. So this is the answer actually. So another name of a kernel, string kernels.
So are other A and D also valid kernel names?
D linear kernel can be, yeah. See, you have to just put n equal to 1. I don't know about exponential trick.
Okay.
So now we have to move to programming questions. Amrita, are you there?
Yeah, I'm here.
Can you help them go through these programming questions? I mean, discuss.
Yeah, you can just show the code. Let us
I'm
discuss.
just putting myself on mute. I'll show the code.
Okay. Okay, so we have The task given is you have to write a function with the hinge loss so that it considers two vectors, test vector y test and the prediction vector y pred, and the function should return you the loss value. So we have seen that hinge loss equation, right? Hinge loss is maximum of 0, 1 minus t, right? So in that sense, for our SVM, we have this hinge loss as maximum of 0, 1 minus x into y, where x is your prediction vector and y is your test vector. So that is the equation that you need to implement here for hinge loss. And since we have the size of the vector is 5 cross 1, so you have 5 elements. So that means 5 samples are given to you with the 5 labels. So we are considering the mean of the value. So that is why we have taken the loss value as np dot mean. So this is how you implement this hinge loss. So if you can see here, the function is defined your your NumPy package is first imported as a prefix code itself so that you don't have to import this package. So we are defining the loss, and this is the equation here. So for every x and y, so for every element, we are considering the maximum value of this function 0, 1 minus x into y. So that is how. So why we consider mean is since we have 5 samples, we are taking the mean of that 5 samples as our loss value. This is very
screen is not visible. Can you go up, please?
Ma'am, there is Srinivasan here. One question, right?
Yes, sir.
So I'm getting this when I do this losses, right? Perceptron and then this and then this, right?
Okay.
Why can't I just take a np dot sum of the second thing, maximum of 0 and 1 minus t? Why should I even do it? Why should I even do it sample by sample?
Loss we consider for every sample, right? For every input sample, every input label, we are considering the loss value.
Okay.
So that is why we have the number of samples is 5. So we are taking the mean of the value for
So why can't I just do a vector?
That's like a mean squared loss.
Yeah,
mean squared error.
See,
loss.
I can do np dot maximum, right? Or
that will give you the maximum of all the losses, right? If you take a maximum value.
No, we can put the axis now. Which axis we need to write?
Yeah. So that's why I get confused, because I tried that part, didn't work. Then I wrote the code like this. You have done it, but slightly different way. I used a for loop, but I actually use a loop instead of using zip, right? But it worked. But actually same this question, right? When do we do it the sometime? When sometimes when we just do the normal vector multiplication. I'm not able to figure out.
Normal vector multiplication in the sense?
Not vector sum. So, okay, I just said minimum of np dot min, right? Min max or whatever.
np dot min of. Okay.
Yeah. np dot of min of 0, 1 minus y pred, right? Whatever the extra t, right? So that part, right? Basically either 0 or 1 minus t. Right. So
you're doing vectorized version of this calculation. That is what you're meaning.
Yeah,
right?
And that did not pass.
Okay, so in there, the same case. So instead of doing np dot min, I think you're taking the minimum value of the loss function. No. So
I did np dot min. I did np dot min.
np dot mean also. You have taken mean value also.
I did sum of the minimum, and then divided, which is the mean. Which is the mean actually. Yeah.
Okay.
So maybe let me post my code and then I find out why this is this way.
Okay.
But here you are doing it sample by sample, right? You are not doing vector addition at all. You're not doing vector manipulation at all.
I am not doing vector addition. Just it is so both case it should be correct only, right? Even if you are taking vector wise multiplication, it takes each of the I think dot products. I think it will give you. For example, if you have x1, x2, x3 and y1, y2, y3, if you are doing vector multiplication, that is what you're referring to, right? X dot y. It will add all the values. No?
Yeah, I mean, better manipulation. What I meant was that 1 minus t, right? I can put that t as a vector. So I thought it should work. Let me see. I might have missed something with some particular NP. So let me try that.
Okay.
Actually, when Mr. Srinivasan said, why can't we do np.sum, right? It actually prompted me a question. In case of linear regression, we said that errors are, if you take the sum of errors, it will be 0. So we wanted to square them and take the mean, right? Is there any rationale for taking mean here?
The same mean squared error, like how we do, we are taking this mean value for the hinge loss. That is what actually we did. Not any particular intuition behind that.
Okay.
Yeah.
In question nowhere written to take the mean, then why you consider the mean? Even in the discourse I have seen, because question has to be like hinge loss mean. Well, when you are talking about the hinge,
telling question should be mean of the hinge loss, mean hinge loss. That is what are you referring to, right?
Because the hinge formula, if you hinge loss something comes max 0 minus 1.
Hinge loss is see maximum. That way, no, you will get only each and every sample. You will get one value for that loss function.
Right.
But here, since we are giving you on the whole, so that is what we thought of taking the mean there.
Okay. That's okay. Then okay. So thank you.
Yeah. So can we go to the second question? So here, I think the question, can you zoom a bit, Girish? Okay. But I could not read the question on the whole. So you are asked to write a function, solve the equation. So this is a simple function which we have to obtain the weight vector, which has this bias as its last element of linear SVM model. And this function will accept only the support vectors and the label vector. So this is equivalent to like having your multiplication, right? That W into X plus B. So like that, we are going to have a multiplication with the weight vector and then using that linear programming. So can you show me the code, Devish? We can go to it quickly. Yeah, so see here, as I already told you, right? Since we are using the support vectors, then we are multiplying that support vector into the given X vector. So that is what it is done. So we are just initially adding this column of ones for our support vectors for that bias element. And that's why we are doing this column stacking of ones. And then we are solving using this linear algorithm. I think we are familiar with solving this equation system of linear equations. So the syntax that we use from NumPy to solve such system of linear equations is np.linear algorithm.solve of s underscore v, that is the column stacked one vector. So that is what is given, and the b value. And for every element, so we are doing this since we are not doing some vectorized form, just element-wise element we are multiplying and then we are adding. So that is why for I in range of length of your X, that is given X vector, you are multiplying that S underscore V element with the given X value to get this W. So that will return your W value so that your test case will pass it. So can you scroll a bit? Just a second. Yeah, that is a simple element-wise solution for this function.
One thing I am not getting the question, last bias, the last number is bias. Where you are using that bias?
See, we have the equation on W transpose X plus B. Since for that only, I think we are using this bias.
This B is your label, right? So what you are doing, you are taking a column stack with ones. So you are putting one column that is getting S underscore B. After that, your equation, which is nothing but Ax equals to B. So I have A, I have B, and you are getting the X. Up to I am here.
X.
Okay, X, I am getting the X, same like our normal.
Here, yeah.
Then you are putting W equals to 0 like. We got the W. This part I am not getting. Again,
Yeah.
X, I.
And Devesh, why you added this zeros like? Can you just confirm?
Let me remember. Okay. So what we did was, see, this is the initial part. So what we want to do is we want to find the W vector, right? And how do we find the W vector? By taking the dot product of SIs along with the X support vectors, right?
Yeah, if you can relate it with a numerical example, right? So
this is how what we do.
Yeah.
So that is the summation is this loop, and this is the product of these. So this is the product of.
So this problem is similar to that of that.
So here also what we do
that
is
we solved, right?
we have this system of equation, and this system of equation ka solution multiplied by the support vectors actually gives you W. Is it making sense?
Is it the question you asked?
Yeah, I'm not getting that from the SBM. You are getting X, and again you are multiplying with the X to SB. I'm getting confused.
So this X, okay. So see, let's try to understand. This A support vectors, right?
Right. Yeah.
B is the labels here. It's not the bias, right?
Okay. Right.
Now with this support vectors, you actually form this system of equations, right?
Right.
And you get these alphas. So rather than using alpha, I actually use this X here. So these are actually alphas, which is obtained by solving this matrix.
Yeah, you can show that PDF so that they will better understand.
And you are putting this alpha into that. Okay. Now okay.
Yeah.
I'm thinking from X again. Why you are multiplying that? Sorry.
Oh, okay. Sorry for the confusion.
Yeah, I should have used alpha. Okay, sorry. So, yeah.
There is one thing. Can you go back to that question so that? Yeah. So our final question that is asked is you need to obtain this weight vector. So if you just zoom a bit, I hope everyone understood now. You can relate it to that solution that we just saw, right? This W equal to that summation over alpha into, yes, if you go to that PDF, can you show that PDF? Yeah, so this programming assignment, we asked just to make sure that you understand this numerical example that we derived. So how do we obtain a simple value of this weight hyperplane? Just to illustrate that we are using this one. Initially, if you use this SVM thing, you cannot find much of hand-coded problems. Right? It's very difficult to hand-code your SVM with large number of data. So that is why we have given some simple problems just to illustrate the how this weight vectors is formed, just to form this hyperplane. So that is a simple question. You can relate it with this practice assignment. So you can go back to
can you tell me how you are get B? Sorry, ma'am. The B, how you get W?
So here now, if you just go scroll up, you'll be adding somewhat down. We add this bias term 1 to S1, right? That part.
1 to S1.
Yeah, here for vector.
Graph, I know it's 2. From graph, I know that it is cutting on 2. Okay, as an boundary.
No. So here the data points are 2-dimensional, right? S1 is 1, 0. And S2 is 3, 1. Now we are adding in bias term. That is, can you see an additional one? That at the last.
Right.
Yeah, this is the bias term that we add additionally for all the vector support vectors, because for our SVM, if you remember from the lectures, our hyperplane is W transpose X plus B, right?
Right.
So we have weight vector components and also this bias component. So we need to derive both this weight and bias.
So you
So
are
that is
telling
why from the data points, you're adding an additional one. Yeah, just to derive the value for the B.
okay, so you are telling from W, I need to derive B from the W transpose X equals to 1, then I need to get the B. Okay.
Yeah, here if you know, you will get 3 values. No? You just take the last value as your bias term.
Oh, that's why you are telling the last value as a bias.
Yeah.
I am confused why you are saying only single value. It has to come 3 value.
Yeah. The first two corresponds to the weight coefficients, weight vector coefficients. The last one corresponds to the coefficient of the bias.
Okay. Now clear. I confused separating, calculating something or what. Okay, thank you.
Okay. So I think we can share this PDF also, practice solution PDF, so that it will help you to solve the graded assignments as well.
So generally it is not shared?
No, generally actually we share it after the graded assignment deadline is over.
Okay.
So now only we are practicing it to release it along with the week's contents, so that it may be helpful for them to solve the graded assignment.
I think, yeah.
Can anyone confirm that the practice assignment, the solution is shared or not? Have anyone seen that PDF document in the portal?
Yeah, it was shared earlier. Please share. Yeah.
Okay, fine. So kindly go through the solution carefully so that you can attempt all the graded questions. Assignments.
Yeah, sure.
It will help you a lot. Okay. So the last question, programming question, is you have to write a class which is fit SVM. So this implements hard margin SVM using gradient descent approach. And that is a class that you are going to define for implementing all the functions for the SVM. And then write a separate function which is named as compute accuracy, so that it returns the accuracy value using this pred accuracy function that is defined inside this fit SVM class. So the inputs are compute accuracy function is xtrain, xtest, and these are the feature matrices for training and testing. And the label vectors are ytrain and ytest respectively. So we are giving you the parameters for the gradient descent approach, which is the learning rate is to be 0.001 and the lambda value is 0.01. That is for the regularization part. And the number of iterations is kept to be 100. So for this fit SVM, what you can do is you can also go through that solution code that is shown in your lectures that sir has taken. So sir is using soft SVM with I think C. If you set the value for C to be equal to 1, which is very, very less, I think. At that time, your margin will be wider. That case also when it corresponds to the hard margin SVM. So you can fit that value, that code also for solving this assignment, or you can also use this code also. So can you zoom a bit for the code, so that they will, yeah.
Is it visible?
Yeah, I hope it is visible now. So you're initializing all the parameters here with that learning rate, lambda parameter, and the number of iterations as given in the question. And initially, you're having no value for W and E. Can you scroll down?
Yeah.
So in SVM, what we have, what we do is we have that two classes to be -1 and +1. So the data, the label data is, I think, 0 and 1. So I'm converting it into wherever you find the value of 0, we are replacing it with -1. So that is what initially done. And then the number of coefficients for weight is equivalent to the number of features in your data set, right? So that's why you're initializing this weight value with the zeros of corresponding to the number of features. So I think, you know, to get this shape, right, x dot shape will return two values. The first one will be the number of rows and the second one will be the number of columns. So the number of columns corresponds to the number of features. So you're initializing zeros for W and B initially so that we can update them via our gradient descent approach. So can you scroll down? Yeah. So here, since we are using this gradient descent approach, we are using each and every data point for on as a whole. As you have learned gradient descent earlier, and the difference between gradient descent and stochastic gradient descent is that your gradient descent will consider all your data, whereas your stochastic will consider one by one. So here I have asked you to do only for this gradient descent approach. So I'm initializing for the number of iterations, and then you are taking this data points, that is index, and the x is in your capital X value, that is the data. And the condition is as follows. As you can remember from our SVM, your y into w dot x minus b should be greater than or equal to 1. So that is what is implemented here. You are taking the dot product with respect to the whole data and then considering this condition. And this condition is derived based on the gradient of that function, the loss function. I think sir explained in the class, right? From there, you are taking this condition. So you are forming this weight vector value here. So if the condition is true, we have one set of equation for W. Otherwise, we have another set, that is W equal to W minus this learning rate multiplied by 2 into lambda into W. If the condition fails, you have to apply W equal to W minus this learning rate into twice of lambda into W minus X into Y. And then we have the formula for B value as well. So this is based on this gradient formula. So once you have fit the SVM, you are predicting it by the dot product of X into W minus B. That is for the predict function. And what will the predict function return? Your predict function will return your sign of the value. That is what your SVM does. So SVM have this W vector and B found using our gradient descent approach. And for any new data, we will return the sign of this dot product and minus B. So these are the basic functions within this class SVM. The next is for finding this accuracy is very simple, right? Accuracy, what you are finding is you are going to just compute what are the data points that are correctly classified and what are misclassified. So based on that formula only, you are going to find accuracy. Yeah.
That's
Yeah, can you show that pred accuracy function?
I think that what you said right now.
Yeah, okay. So yeah. So accuracy is the total number of points that are correctly classified divided by the grand total of points that are available in the data set. So your S gives you the number of points that are correctly classified. And N is here, I think, the number of points in the data set. So these functions are written inside this class as fit SVM. And once you complete this fit SVM class, you just write a compute accuracy function so that you pass on all this data points and label vectors. and return the value of that accuracy. That's all. So if you scroll down a bit, you will have that compute accuracy function. So you're just fitting the SVM and then predicting using that pred accuracy function and returning that value. That's all.
Yeah, I think we have discussed
These
everything.
three are the programming questions, I hope. So tomorrow in Solve with Instructor session also, we will try to implement this SVM from your end also. We will give you tasks based on that, and then you can also code yourself along this.
Should we close the meeting or are there any doubts? I think we have already exceeded the time by 20 minutes.
Yeah, time is like, do you have any doubts?
Okay.
Yeah, I think today we can close the session on this weekend activity and practice.
Okay. Bye everyone.
Thank you everyone for participation. Thank you, Devi.
Thank you.
Thank you.